So you can see how this can be a direct surrogate for quantum mechanics if you have enough training data. And instead of having inference times of hours to days, you have inference times of milliseconds. So you can see how this is completely game-changing. So it's a pleasure to introduce our next speaker now, Aron Walsh, who's a professor of materials design at Imperial College here in London. He's also the Chief Scientific Officer at CUSP AI, which is a London-based startup developing AI techniques for materials. So he was awarded the EU 40 Prize for his work on the theory of next-generation solar cells, and also the RCS Corden-Morgan Prize for contributions to computational chemistry. So today he'll be speaking to us about the role of AI in materials on demand. So thank you for the kind introduction. It's great to see so many people here. I think we're really covering a wide range of length scales today. So I'm going to be taking you from galaxies to atoms. So quite a jump in terms of concepts. But I'll do my best to make it engaging. So I would say I'm a chemist who likes computers. And so that got me into this field. And I would say the hook is very strong. So when you start to learn about the concept of computational chemistry, it's that we have access to equations that describe every possible chemical bond, every structure, every property that emerges. So they're all the results of quantum mechanics. And so maybe a century ago in the Royal Society, this was a hot topic for debate. So this is a quote from Paul Dirac, who won a Nobel Prize in Physics. He's originally from Bristol. And he developed the relativistic quantum mechanics and beautiful equations that in principle describe all chemistry. But you have to keep reading in his paper. Of course, the difficulty is that the equations are too complicated to be solvable. And I think in many aspects of science engineering, we face this challenge. We have master equations that can describe many types of processes, but we can't actually solve them. So then there was a century of activity trying to approximate, so come up with simpler equations that we could solve, and also take advantage of hardware. So the first digital computers were largely used for quantum chemical applications. Now CPUs, GPUs, quantum computers are all harnessed for these types of tasks. But I would say even now, it's impossible to solve these equations exactly for systems of relevance to the real world. So what we have to do is approximate. So the start of my career was largely focused on quantum mechanics and dealing with wave functions. So this is the nature of electrons at sort of nanometer length scales. So when you bring atoms together, what types of bonds form? What type of properties will those bonds have, for example, when you shine light or you apply a stress? Very predictive for simple systems, but it's difficult to scale. So then one of the approaches is that, okay, let's disregard the electrons and treat atoms as spheres. So spheres connected by springs. And then that brings you back to Newtonian mechanics. And suddenly you can do much larger complex simulations, but you're losing some of the predictive power. So you can't really describe sort of bond formation or breaking using these classical models, but you can still do some very useful things. And then something else came along. So I guess about a decade ago, there was the translation of machine learning techniques from computer science into my world. And the concept is a little bit different. So instead of thinking of atoms as just hard spheres, we could think of them as vectors. So vectors that encode information. So we could start to learn representations of atoms that encode information related to bonds, information related to excited states. So the goal at the end is sort of having a set of methods that have the predictive power of quantum mechanics, but have the computational speed of classical mechanics. And I think that's one of the roles that machine learning has played in this field. And so immediately what it means is that you can start to run simulations of much more complex systems with this predictive power. So on the screen you have two simulations. On the left is a simulation of a solid electrolyte in a sodium-ion battery. So this is a very active field of research in materials chemistry. We're looking for replacements for lithium, because lithium is getting expensive and quite difficult to source, and replacing it by sodium. And instead of doing tens of thousands of experiments, you can start to run simulations to navigate the space and identify targets very quickly. On the right, you have a simulation of it's a piece of a solar cell, referred to as a perovskite solar cell. And we're quite interested in this case in how the material actually operates at room temperature when light is present. And the colors represent sort of local structure. And you can see there are these very local domains that form and break up that we can connect to the photophysics of these materials. So on one side, we can do very fancy simulations. It's really impressive. But I think that's not everything. So what gets me very excited is this concept of materials design or inverse design. So whatever application you think of, it's determined by, it's formed of materials. Those materials have properties that either limit the performance, or you might want to replace a material because you cannot source the elements at the scale that you need for deployment of technology. So often we can articulate a set of properties we want in a material, and the challenge is to identify the candidates that actually give rise to those properties. So it's a classic inverse design problem that's very difficult for traditional techniques. So how do you map from a set of properties to a material? Well, we have some sort of magic blue box here, which is the materials AI. And how I view this, we essentially have 4 components that people around the world have been working on. So we need data sets. Of course, you need data, the connection between properties and structure of materials. You need automation. So this could be automation in terms of simulations, so building up large synthetic data sets. Or it could be automation in terms of experimental capabilities to test and realize these materials. Models, so a variety of models to identify correlations within these large data sets. And then finally, you need to converge towards an optimal solution. So that brings in selection algorithms, so it could be Bayesian optimization, could be reinforcement learning, or some other approach to navigate such a large search space. And yeah, many developments happening, people making different choices for each of these sort of gold sections. But what I'd say, the problem is even more subtle because we have constraints. So depending on the application you care about, you're going to think about the cost of elements, you're going to think about the toxicity, the availability. So we're dealing with a very skewed periodic table of elements. So it really depends on the application, but you might very much care about element availability, where those elements are sourced, and can they actually be sold as a device. So these are factors that you can start to build into the models to say, okay, we cannot access every possible combination of elements. If you want to build a battery technology, for example, you're going to need a lot of those elements to actually scale up to production. And then on the other side, we have to think about sustainability in terms of computing. So I really like efficiency in my research. So it's trying to be smart in the simulations and workflows that we deploy. And I think there's been a lot of progress. I think AI gets some negative light in terms of energy usage. But in terms of scientific computing, it actually can be very efficient in terms of solving problems. I think there's many developments in more efficient hardware, actually putting supercomputers in places that make sense. For example, in Northern Europe, where you have a lot of hydroelectric power, and the heat can actually be useful to local communities. And I really like this list on the left. It's the Green 500 list. So it's the greenest supercomputers in the world that are also sort of substantial in terms of computing power. And interestingly enough, the top 4 systems are all based in Europe. So there's been a real push towards sort of sustainable computing. And number 4 is Isambard AI, which is the UK national GPU system that's based in Bristol. And we've been using that for actually a lot of our simulations. So that's my preamble, and I basically have 3 sort of short sections. I want to introduce machine learning for materials, so how we actually approach that problem, how we navigate these large shared spaces, and then moving towards applications, how we actually deal with this inverse design problem at the end. And I think in this room, there are many experts of machine learning, so beyond my expertise, but I'll start with a very simple definition. So to me, we're dealing with algorithms that learn from training data, and we want to build a model that can make predictions. And I think the prediction part is really important. So it's not just data fitting. We want a model that can actually do something useful. So from my perspective, as I said, I started my career working on quantum mechanics. The basic workflow here is that we have inputs that are at what atoms we have, where they are in space. We then solve a set of equations. So it could be some approximation of the Schrodinger equation. And then we have outputs. So it will tell us the energy of the system. We could be interested in mechanical properties, optical properties. And we would use supercomputers for this. So Archer 2, National CPU Resource, spends a lot of time crunching the matrices associated with these types of Hamiltonians. Machine learning gives us a different approach because instead of solving these partial differential equations, we can train a flexible function, or at least if we're doing supervised machine learning. So we have, in this case, a feature vector, x, that has to encode the chemistry of our system. Then we're going to learn a function that takes that x and makes a prediction. So you can see how this can be a direct surrogate for quantum mechanics if you have enough training data. And instead of having inference times of hours to days, sometimes a week for a very large-scale quantum mechanical calculation, you have inference times of milliseconds. So you can see how this is completely game-changing. And once you start to do machine learning, it's very difficult to go back to quantum mechanics, to be honest. I don't want to submit jobs to a queue and wait 2 weeks to get results. I want something fast. But something I found is really quite key is how we choose this input vector x. So how do we encode chemical information into a numerical form that's suitable for machine learning? And then you think, okay, what do chemists do? And so you go back to the 19th century, you had people like Dalton in the UK thinking about the relative weight of atoms. And then Mendeleev started to arrange these atoms into sort of periodic trends, and that's our periodic table. So that's thinking about a single feature, which is the relative atomic weight of each element. And you can do that in terms of machine learning. You can have like a one-hot vector that just describes which element is present, but you're not really encoding anything of sort of chemical interest. But if you look at a modern periodic table, there's a lot more information. So we have atomic number, atomic mass, we have electronic configurations, we have the standard state of the elements, is it solid, liquid, is it gas, many different properties of those elements. So then you can think of a starting point that is not just a categorization of different element types, but we start to encode some of this information to give the machine learning model sort of a helping hand. So I'd say the first wave of activity in my field was dealing with these hand-built representations. So you think of defining a feature vector that encodes information about each atom. And so you can do that by working with standard properties of the elements. So one of the popular models about 10 years ago was called MagPi. And so it basically represents each element of the periodic table is a vector, but each component of the vector has a physical meaning. So it's the atomic number, it's the atomic weight, it's the melting temperature of the standard state of that element. And it turned out that this was a very effective way of building supervised machine learning models. So much better than just starting with a one-hot vector. You could build models with much higher performance. But that was 10 years ago, and that was sort of in the low data limit, where there was a large focus on building simple, fast, interpretable models. But I would say things have shifted a little bit. And I would say the standard now is thinking of learned or distributed representations. There's a range of approaches that have been developed. So one of the really nice reports from a colleague or a collaborator of mine, Anubhav Jain from Berkeley, he took 1 million published papers and took the abstracts of those papers from material science and used a word-to-vec model from Google. He calls it mat2vec, and basically learned a representation. So based on the pairing of words, so maybe you're interested in copper. Copper appears in abstracts saying copper conductor, copper solar cell, copper melting. So from those pairings of words, you can start to learn a representation. And the really interesting thing, so it was an unsupervised study sort of learning these representations, but they showed it had predictive power. So they could actually make predictions of applications of materials in different domains, even though they hadn't been studied before, but because of the correlations in these learned representations. So that was really nice. We've done a little bit of work on looking at structures, so taking some large structure databases. We can do what's called structure graph pooling. And again, we learn a 200-dimensional vector based on the connections of atoms that are present in experimentally observed materials. And again, we found these are really useful starting points for particular property prediction models. I'm a big fan of open source software. And we actually built a tool. So Anthony Onwally was a PhD student at Imperial. He's now a machine learning engineer at Materials Nexus, which is a startup in London. It's a tool called Element Embeddings, and it's just a simple tool for being able to play around with these types of representations. So we tried to collect many representations from the literature. You can look at correlations between them. You can generate them very quickly. So that's available online. And maybe the last thing I'll mention, so I would say what's happened over the last year is a big push towards foundation models in my field. So taking much bigger data sets. Interesting point, Meta has used hundreds of millions of CPU hours to perform quantum mechanical simulations on hundreds of millions of materials, molecules, polymers, crystals. They've made all of that data openly available. So this is a really great playground for building large foundation models in this field. But this concept of models trained on differing data sets with different architectures for chemical systems, are they all describing or learning the same thing? So I guess in different domains, you've probably come across the concept of Platonic representations. So if you're getting some convergence in what's being learned. And in our case, this is 3 different models. We're just looking at the embeddings that were learned. The colors represent the traditional categorization of element types. And you can see the maps look very different because they're very different models. So you have a graph neural network versus a transformer, for example. But Zhenju Li, who's a research fellow at Imperial Global Singapore, so she had the idea from looking at what was happening in large language models to use this idea of anchors. So that's basically we define a list of reference materials and use them to anchor the latent space. So you perform this sort of coordinate transformation that takes very different models and you try to map them onto a common space and see if they actually agree. And the agreement was much better than we expected. So here on the 3 different rows, you have 3 very different types of models in terms of, well, the first 2 are a little bit similar. It's a small version versus a medium version. And then you've got a very different model on the bottom. But you can see these have been trained independently on slightly different data sets, but they start to learn a common representation of how atoms are distributed. And this becomes quite interesting because we see some models trained on language, some trained on energies, some trained on properties. They're all giving pieces of a puzzle. And using this type of approach, we can start to patch or translate information between different models. And I think that's something that's quite interesting. Okay, so that was sort of a little bit of background in terms of the general approach for machine learning materials. But now imagine we want to, going back to my title, we want to tackle materials on demand. So we need to navigate a space of possible materials. This is another quote from the last century. And already at the time, people realized there was an indefinitely large number of compounds built of atoms. And to chemists, usually you think about sort of complexity in different ways. We can have complexity in terms of the number of elements present. So you can go from elemental systems like carbon through to 4, 5, 6, 7, 8 component crystals. That's just based on combinations of elements. But you also have complexity in terms of the structures that form. So in some simple cases, you can have very dense structures that are close packed. In other cases, you get much more open structures. And this is a vast landscape to describe. So I would say traditionally, even in the subdiscipline of materials chemistry, people would focus on a subclass of materials and become an expert on that subclass. And very few people have a broad knowledge across from metals to ceramics to polymers, for example. But we want to navigate this space. The challenge is in material science, when you get into the details, you're dealing with composition, structure, processing into how you make a material, and also then the properties of that sample that's produced. So it becomes a very high-dimensional, complex problem. And I'll just give you a feeling in terms of numbers by just focusing initially on composition. So imagine I want to form a 6-component material. So I'm going to combine 6 elements. They can combine in different ratios. So then I have a particular search space that I can navigate. So I can start to crunch those numbers. And of course, as you'd imagine, you get this exponential increase in the number of possibilities. So if I go to a 6-component crystal, I have over 10 to the 13 possibilities in terms of combinations of elements. That's if I'm just being very naive and saying I can combine any I can have any combination of elements from the periodic table. If you look at what's been observed, so ICSD is the Inorganic Crystal Structure Database. So that's collected a subclass of materials called crystals. And you can see the observed crystals peak at 3 component. So one of the challenges in materials AI is, can we look at the difference between the orange and blue peaks? So that's sort of our missing space, our space of materials that have not been made yet. Can we identify what parts of that space should we actually target? What parts have interesting properties? What parts are likely to be synthesizable in the lab? And so that's one of the big goals in this field sort of right now. One of the ways I've done it sort of on the academic side in the past is using chemical rules. I really like minerals. So if you go to the Natural History Museum, you'll see many samples of Spinel. So Spinel is sort of a cousin of sapphire. In this case, it's magnesium aluminum oxide. It forms a very special crystal structure. It's used in batteries. It's used in solar cells. And we're quite interested in looking at the space of possible spinels. So we produce these sort of maps, which is element versus element. Red is a spinel that's been observed. Dark blue is a case where we say there's a high probability of that spinel forming. And white, we're saying there's no possibility in terms of the chemistries just don't match. So we have this sort of hierarchical approach where we sort of try to narrow down the combinations, and in this case, identify new possible spinels that we could actually try to make in the lab. And how we do this, again, another open source tool, in this case called SMACT, for navigating chemical space. This was actually when my group started to use Python. This was our playground for teaching new students. So we'd get undergrads from chemistry. They would learn Python, and then they'd have to try to translate some rules from textbooks into a code. And so this was really a toy code for our group. But then it started to become really useful in the AI community because you have many computer scientists that don't know chemistry. So having codified rules becomes quite helpful. So now, like, there's over 5,000 downloads a month. And then we have to actually maintain it, which is a bit of a pain. But there have been many contributors over the years to this package. But basically, it allows you to look over these combinatorial spaces. Okay, going into the last section, so towards inverse design. So the challenge here, I said, we want to design a compound that has particular target properties. If I'm focused on crystals, how we usually represent a crystal, there's 3 parts. We say what atoms are present, where are they in space, and then what is the box, the repeat box that defines that crystal. So this is AXL, 3 different parts. And you can see already it's going to get complex because atom types, it's a category, and fractional coordinates can be sort of continuous positions in space. So for model building, this becomes a little bit painful. But the idea is we can represent a material as Z, which is a set of AXL. And wouldn't it be great if we could sample a distribution of all the possible crystals and condition it towards particular properties? So yeah, the probability of Z given a certain set of conditions, and they could be the properties that we want in those particular materials. So that's the challenge. And it turns out this is where generative artificial intelligence comes in. So this is something we couldn't solve before. So there are no viable inverse design approaches in this field. But we can use neural networks as a way to encode these features of a crystal into a form that's suitable for generation or sample of new compounds. So you might think we have a distribution in terms of the range of known materials, many different features of those, but it's a very messy distribution. You've got so many different types of materials, different stoichiometries, different properties. But if we can encode it into a much nicer distribution, we can start to sample. And that's where this field has sort of moved over the past few years. And our first sort of step into this area was a couple of years ago. And we're really inspired by the work on text-to-image models, right? You can say you want a mouse riding a car in the Royal Society, and you'll generate an image of that. And can we do the same for crystals? So can we have a text prompt and actually produce a material at the end? So this was the challenge. Hyun-Soo Park was a postdoc who led this project. He just moved to Lila Sciences in the US last week. The idea was we had to start by building a representation. So we had pairs between text descriptions of materials and structure. And in this case, structure was in the form of a graph neural network. Atomic systems map very well onto graphs because you have atoms or nodes and edges or bonds. So there's a very nice mapping. So we basically had a contrastive learning problem where we had these text crystal pairs, and then we can use that as a conditioning signal for a denoising diffusion model. So that's the basic idea. So you start with a random material. You see here, random is just blobs randomly placed in space. And then over 100 steps, it diffuses to quite a reasonable representation of a material. So this is a denoising diffusion approach. It turns out it's very, very efficient. So of course, training is a little bit heavy. But in terms of deployment, this is something you can run on a laptop. And you can start to sample structures for different compositions over quite large spaces. So these triangles at the bottom are essentially ternary phase diagrams. So they're 3 different components. We can start to navigate those spaces very quickly using these types of models. And honestly, what would have been a PhD even 5 years ago can now be run in a day in terms of navigating such a space. And the field has really moved that quickly. But we weren't happy. So actually, Microsoft last year released a really nice model called MatterGen, which is also a denoising diffusion model. Hyun-Soo was very competitive, and he's like, we can't let Microsoft beat us. So we needed to change architecture. So we started to shift from real space to latent space. So all of those, our initial models were essentially doing generation in a space of Cartesian coordinates. So then the chance was to go into latent space. So using a variational autoencoder to define a latent space for crystals. And then we do our generation within that latent space. So the number of dimensions gets reduced, so the models are much faster than what we had before, but they're also easier to control. So we also integrated with reinforcement learning. And it turns out the first models we had using this approach, they were worse than the real space, but once you add reinforcement learning, they just become incredibly good if you can avoid the issues with reinforcement learning, because the models cheat whenever they can. So you have to be very specific with your constraints and with your assessments and to make sure they don't give you small variations of the same material. So it took a lot of effort to make sure that the outputs were diverse enough to actually satisfy a materials chemist. Okay, so I'd say right now, so when we're navigating these spaces, there's sort of 2 approaches. I was at a conference in Spain, so in Bilbao last summer, and went into the Guggenheim Museum. I saw this, and if you go to materials AI conferences, you'll see a lot of these, and it's basically a funnel. That's how I view it. So basically, you put a large database in at the top. It might be 1 million materials. You then perform a lot of calculations, assessing the properties of those materials, and you hope something comes out at the bottom. And it could be you've done 1 million calculations for 2 candidates at the end. And it's definitely a feasible approach. It's taking advantage of large databases and increasingly fast surrogate models. But it's just not very elegant. It's like a lot of wasted calculations that are going through this pipeline. So I think we can do things a little bit better. But I would say this approach does work. So using the tools I mentioned earlier, this is just another plot to impress you. So this is a map of a particular chemical space against, again, element versus element. We were looking for 3-component crystals where we could remove one of the components and form a new layered crystal. Because sort of layered or 2-dimensional systems are really a hot topic in material science. So we did this type of screening, and collaborating with a group of Woo-Young Shim from Yonsei University in Korea, his group has synthesized over 12 new layered crystals. They didn't exist before. They don't occur naturally. But following our guidance, for example, in this case, it's taking a 3-component crystal with gallium and arsenic, removing the 3rd component, and you form a completely new structure for gallium arsenide that's different to what's observed naturally. So it opens up sort of the playground for forming these low-dimensional crystals. And this is a case where the hierarchical screening worked quite well. But I was still at the Guggenheim, and then I went into a different room, and I saw this. And I was like, what does this remind you of? So this, if you do any plots with T-SNE or PCA, this looks like a latent space, right? So this was on my mind. So moving from this sort of hierarchical screening to think about integrated design. So instead of separating all of our filters, let's throw everything together. And so can we navigate the space of composition and structure and processing and properties and find good solutions? And I would say where the field has been going now is dealing with scientific agents that can navigate these complex spaces. So where standard sort of human workflows fail, we can start to have agents that learn. So you start sampling this space, you make choices according to the results that come out. Agents that can access tools, so they could run a quantum mechanical calculation, they could run a machine learning surrogate model, they can use a generative model, and they can refine with feedback. And I think this is where things get very interesting. So we don't have to compute this whole space. We can start to navigate that space to try to find good solutions as efficiently as possible. And so there's a lot of excitement building around this topic right now. And that's led to me this year. I joined CUSP AI, which is an AI for materials startup that's founded in Cambridge, so by Chad Edwards, and also by Max Welling, who's one of the pioneers behind generative AI in Amsterdam. And the interesting thing, so it's working on an agentic platform for materials discovery. I helped launch a London office in January. On January 2nd, there was 2 of us sitting in King's Cross, and now it's up to about 15 people. And it's just incredible working in a diverse team of computer scientists, of machine learning experts, domain scientists like me, so like chemists and physicists. And the pace of development is really incredible. But I would say the other side to this story, and I didn't really have time to go deep today, is thinking about physical world integration. So there's a lot of activity happening on the automation side of material science, a little bit slower than in biotech, for example. But this is one case that I've been involved in. So it's called DigiBat. This was part of a strategic equipment grant funded by UKRI and led by my colleague Magda Titerici, and with Sam Cooper, who's in the audience, as well as Ifan Stevens and Mary Ryan. And the basic idea was building up a set of robotic platforms for battery discovery. So you want to be able to make materials to turn them into battery cells and actually test those cells in an automated fashion. And so this is hosted over in the South Kensington campus, and you can see sort of the illustration here. The timeline has been quite long, so it was funded 3 years ago, a very long setup process in refurbishing a lab, on dealing with vendors. It's fully operational last summer, and now we're just finishing a campaign to produce open battery data. And this is incredibly exciting. So these are very complex processes. You have many steps, you have many parameters, but there's very little open data for us to actually train models. So there's been a team working really hard and dealing with sort of preparation and assembly. And some of the fun tasks we can do is, for example, comparing the performance of a human expert who knows how to make a battery versus the learning rate for an automated system. And so that's the sort of the blue versus red in this side. So again, this was supported by UKRI, and there's going to be some really nice open data sets coming in the future as part of this project. And that brings me towards the end. So I would say my outlook for materials AI in the UK is that it's very exciting. I think there's a lot of activity right now. So the Henry Royce Institute have been trying to put forward a national roadmap for materials 4.0. So that's sort of the digitization of material science and thinking about smart automation. There's a lot of activity on the chemistry side, which a lot of the underpinning tooling. So the Alchemy Hub shared between Liverpool and Imperial College and involving many groups around the country is doing a lot of really nice work. There's an incredible emerging industry. So just in London and materials, so I mentioned CUSP, there's Polaron. Sam is actually one of the leads at Polaron working on microstructure of materials, and Physics X dealing at even longer length scales. And this is just a few. There's probably over half a dozen companies that have appeared in the last couple of years working on AI for materials only in London. which is quite incredible. And then nationally, GPUs are essential, of course, for training as we're moving towards the deeper models, foundational models. So Isambard has been really valuable. And also ARIA and Encode for supporting fellowships in this area. So it's actually quite challenging to get some of the high-end people from AI to join the sort of the material science campaign, because usually researchers in material science are paid much less. I think that's sort of one of the facts. And ARIA, with this Encode Fellowship, is trying to attract those people. So enabling experts in AI and machine learning to tackle problems of relevance to science, including physical science. And I think that's really important because the field can move forward much faster. But otherwise, yeah, thank you for your attention.